All right, here we go. This is our last little intervention thing for the Easter term, of the Easter holidays, even. I decided to pick one that can be split up into multiple different levels of difficulty, which is ratios. And the topic ratio is incredibly diverse. So rather than trying to literally pick apart everything to do with ratios, which, we could be here for some hours, I decided to focus on three things in particular. Okay. And in each section of this intervention, there will be questions to focus on those three aspects. So if you want to focus on combining ratios, there'll be a section for you. If you want to focus on dividing ratios, there'll be a section for you. And if you want to think about something which is considerably tougher, which is the equality of ratios, then that final section will be for you. And that final section deals with a few algebraic problems, so it really does push things beyond the kind of crossover zone. So you could almost think of these as like your combining being like the foundation crossover side of things, the dividing being the crossover intermediate section, and then the equality of your ratios being the higher tier thing that we should strive for. Okay? So, we're going to start right at the very beginning, right at the very start. We're going to look at combining ratios now. Now, first of all, we need to think about what does a ratio actually tell us. Okay? A ratio, for example, a ratio 2 to 1, tells us that for every two of our left things, we need one part of our right things. And we can often visualize this in terms of boxes. So we would need two boxes to make up our left-hand side and only one box to make up our right-hand side. For every two parts we have of the left, we have one part for the right. Okay. Now this ratio is written in the form n to 1 because this right-hand number is 1. The one underneath is in the form 1 to n because the left-hand number is 1. You can have fractions in your ratios. It's not often that we would write decimals, especially decimals that are repeating, but we can use fractions in our ratios. So this is telling me that for every one box I have for the left-hand side, I would need 3/5 of a box on the right-hand side. Now, what's important is that we can take this and say, well, actually, we could scale it up. So instead of 1 to 3/5, I could times both sides by 5 to get 5 to 3, which is something which is considerably easier to manage. 5 boxes to 3 boxes is considerably easier to manage than 1 to 3/5 of a box. Okay? But this is no longer in the form 1 to n because neither of these numbers are a 1. It is in its simplest form, though, because I can't divide by anything here that's a common factor. Okay, there's no common factor between 5 and 3, so this cannot simplify any further. Okay, so that's the kind of like basic ideas of ratio, that for every two parts of the one bit, we'd equal one part of another, or whatever those ratio numbers are. Okay, and thinking about parts and boxes are going to be quite key for this if your understanding is not quite where it should be. Okay, so first things first, combining ratios. We might need to combine two ratios in order to work with a larger problem. Okay, we might have like a total amount for 3 separate items or 3 separate things, and we're wanting to know how should we split up amongst those 3 separate things given 2 individual ratios. Now the way we can do that is that we need to look carefully to see what is the letter that is shared within those 2 ratios. What is the bit that they have in common? Okay. Well, in this ratio, the b's are the bits that they have in common. Okay, and we can see that the 5 in the first ratio should match up with the 3 in the second ratio. Now, we can only combine two ratios if the common part is equal. Okay, so I can only write this in the ratio a to b to c if my b parts of that ratio are equal. And I would do that just by multiplying them up, by making them equivalent. Number that 5 and 3 both go into 15. So I should times my a to b ratio by 3 on both sides, and my b to c ratio by 5 on both sides. Kind of like you would if you were doing a common denominator for adding fractions or something like that. So my a to b ratio, instead of 1 to 5, would become 3 to 15. And my b to c ratio, instead of being 3 to 2, is going to become 15 to 10. Because I timed both of those numbers by 5. Now, because those b parts are the same, I know how each of these things will match up. So my ratio of a to b to c is going to be 3 to 15 to 10. Okay, and I can't simplify that any further because nothing goes into 3, 15, and 10. Something goes into 3 and 15, something goes into 15 and 10, but nothing goes into all three. Okay, so one for you to have a go at over here, just individually, reveal it. There you go. And I'd like you to have a go at that. You can pause the video if you want. Okay, you should have paused the video there. I'm now going to go through this solution. Again, first thing we check to see which part the ratio has in common. It's the b's again. Okay, I clearly don't have an imagination. I'm looking to make those b parts the same, which is the 7 and the 4 for these ratios. 7 times 4 is 28, so that will be my common number. I'm going to have to times the 7 by 4 and the 4 by 7. So a to b is going to be the ratio 6 times 4 is 24, 7 times 4 is 28. And b to c is going to be the ratio of 28 to 3 times 7, which is 21. My combined ratio of a to b to c is then going to be 24 to 28 to 21. Okay? So that might be an aspect of problem solving that we would need to deal with a bigger problem overall. Okay, thinking if you've got three ratios, three parts for a triangle, thinking about their sides or their angles, you might have a ratio of two sides and a ratio of another two sides, and then look to try and combine them to work out the length of each of the three sides. And what this would usually be combined with is what I would call a division problem. Okay, which is the type of problem that we're going to look at next. Okay. So if you want to practice what we've done here a little bit more, just to get your head around it that little bit more, you can tackle these questions in the PowerPoint, and you can click on the answers box to reveal the answers so that you can check them as well. Things get a little bit more difficult getting to question 5, okay? And we'll deal with some of these things a little bit later as well. Okay? So if you want to check out these, go for this slide here. But what we're looking to do is we're looking to maybe think, if I've got my ratio together, how do I then use it to think about doing some extra problem? Okay? And that's where we would do like a ratio division or something like that. And we have done these many a times before, but it's always worth a reminder. Okay, so I've got two questions here which are very, very similar, but how you approach them and what you do with them will yield two very different answers. We've got two people who share some money in a ratio of 5 to 3. One of them has got £240. We want to know how much does the other person have. Now, if your understanding of ratio isn't as awesome as it might be, what you can do, and what I sometimes encourage people to do, is to think about this in terms of boxes. Okay, we've got one person that has 5 and another person that has 3. Okay, we've said that this person at the top, this person has got £240. And they've got 5 boxes to split that up into. So to find out what one box would be, I would have to do 240 divided by 5. Now, you might have just said, well, this person's got 240, that's what the amount in the ratio is, so I'm going to do 240 divided by 5. And what that does, it works out what one part or one box in this ratio is. 200 divided by 5 is 40. 40 divided by 5 is 8. So in each of these boxes is going to be £48. Now, we know that one part is common between both parts of the ratios. We know that for every 5 parts in the top one, we have 3 parts in the bottom one, and each part has the same value, 48. So I know that then my second person has got 48 times by 3 because they have 3 parts of that ratio, which is going to be 144. Okay, and box diagrams like this, if the ratios aren't too big, can be very, very helpful. If the ratio numbers are quite large, then might not be the best thing to do. You might need to think instead about, okay, what would I need to divide by to get 1 part? What would I need to multiply by to get 3 parts? Okay. Now, having seen that method, I want you to take a look at this second question underneath, okay, and see if you can do something similar. However, there will be one part to this question which will change the outcome that we want. We want a different answer to what's above. Okay, so I'm going to ask you to pause the video, see if you can set up the question like we've done, and see if you can carry it through to the end. When you have done that, feel free to unpause, and then I'll be looking through it. Okay. So, like before, we've still got our 2 people, so I'm going to label which one is which. We've still got the same ratio, so I know that my top person has got 5 boxes, and my bottom person has got 3 boxes, just like so. But this time I know that my first person has got £240 more than my second person. Okay, so these parts of my ratio here are £240. Now, you might have been able to tell this from the question because in looking at the ratio, we have 2 parts, which is more, and we've got £240 more. So those 2 parts must have been worth £240. If 2 parts are worth £240, 1 part is worth £120. And so each part in this ratio must equal £120. We're then asking the same thing. We're asking how much does our second person have? And in this case, we can see that this second person has £360. And we can see that just from shifting where that piece of information goes, where that 240 goes, we get very different answers. Now, using the box method is nice. It's quite visual. It's quite then easy to see where all the information goes. But for larger ratios, say if you had a ratio of 21 to 23 or something awkward like that, drawing out 21 boxes and 23 boxes is not a good use of time. So then I would want to know, okay, what am I having to divide by? What am I having to multiply by? Okay? And that's where being able to say something like, I don't know, 240 divided by 2, because there are 2 parts, is 120. I want to know how much does the second person have. My second person has 3 parts, so I need to do 3 times 120 to get 360. Okay? Taking something which is quite visual to something which is quite abstract. Okay? Just looking at the numbers that are involved. And again, if you want to practice these types of questions, I've only put 4 up for these because really, once you get in the habit of what you're doing, you're just kind of doing the same things over and over again. You're just looking to see where does that bit of information go. Okay, that's what you're looking for in each of these cases. Where does that bit of information go? And in some cases, you might need to think, what do I know about the situation they're giving me? Okay, for instance, you might think that angles within a pentagon add up to 540 degrees. Or you might think that, I don't know, all of the sides added up together equals a perimeter that they've given you. Okay, something like that. Okay, and again, when you want to check your answers, you can just click on this box here. The final part that we want to look at, an equality of ratios, is something which you will need to kind of get your head around a little bit. Okay, and the way that I'm going to get you to think about this to start off with is to think about a very simple ratio. Okay. I'll come back to the boxes in a second. I want to just look at this first. So, let's say we've been given 2 different amounts, an A and a B. We're going to deal with algebraic terms for this. Okay. And I said that it's in the ratio of 2 to 1. Okay. We would want to think about how can I make these 2 parts of the ratio equal. Okay. Now, what I can't do is I can't just say A is equal to B, because that's clearly not the case, because A to B is in the ratio of 2 to 1. Okay, and A cannot equal B if they're in a ratio of 2 to 1. That just simply does not make sense. Okay, what I would need to think about is how can I make these 2 things be equal? What I'm going to do is I'm going to look at this. How can I make it with this ratio that I've got the same thing on both sides? Well, what I could do is I could say, well, let's divide that bit by 2. So then I would have 1 to 1. Okay, then I would have the same thing on both sides, and I could say that the left side equals the right side. Okay, and I know that I've not done the same thing to both sides here. I'm not looking to keep this balanced. I'm looking to make it equal. Okay, I'm not looking to preserve the imbalance of 2 to 1. I am trying to make it equal on both sides. Okay? It's almost like you're thinking, how can I get this ratio to be 1 to 1? Now, if I get rid of the just abomination was what I've written before, I can now think, how can I make this be equal? Well, I'll just do the same. So I can divide that by 2 and get A over 2 equals B. Okay? So then the A, which divided by 2, will effectively be a 1 part in that ratio, and the B, which I didn't divide, will still be a 1. Before we come back to the lower half, I'm going to take us back to the boxes idea now. So if we had A to B, which is in a ratio of 2 to 1, the only way that I'm going to make it have the same amount so that they are equal is if I halve the number of A boxes. So if I halved it and went, there we go, I'm going to chop it off in there and I'm going to discard U, I would have the same number of boxes, so then I could say that the A's will equal the B's. Okay, and that's why we divide it by 2. Now let's take a look at that second one down here. This says that x to y is in the ratio of 5 to 3. Now, we can't just write x equals y because that's just completely and utterly incorrect. What we have to do is think about how can we make this a ratio where they are both equal. Okay. Now I could say, well, in this case, I can divide the right-hand side by, the left-hand side by 5 and the right-hand side by 3. And I could do that. And then I could say, okay, x divided by 5 would be x over 5. And y divided by 3 would be y over 3. And you might look at that and go, fractions in equalities? I don't quite like that. Well, if that's the case, let me give you a second way of thinking about this instead. Let's pick a different color. Let's go mid-blue. Rather than thinking of it of a 1-to-1, what I can just do is just pick a number that I know that both of these parts will go into. So rather than scaling down, I can scale up. Now, 5 and 3, we all know that they both go into 15. Okay, now 3 times 5 would get me to 15, and 5 times 3 would get me to 15. Now, you can see what's gone on here. Instead of dividing by 3 on the right-hand ratio, I have timesed by 3 on the left. Instead of dividing by 5 on the left, I've timesed by 5 on the right. There's like a little opposites thing going on here. And what I would have for that is taking the x, timesing by 3 would give me 3x, equals taking the y and timesing it by 5. Now, the really cool bit of this is seeing how the red and the blue link up. Now, if you can spot how the red and the blue link up, that's really good, because you're then making the connection between your two equations. And you can see here that I have timesed both sides by 5 and timesed both sides by 3, so that 3 comes up here and the 5 comes up there. So times by 5, times by 3, times by 5, and times by 3. Okay? Whether you take the approach of scaling down or scaling up doesn't really matter. It will do the same thing in the end. Okay? And I've got about time to do maybe one example of how this would work in terms of a actual algebraic problem. Okay? So we're going to take a look at that now. So, we want to work out the value of x such that x take away 20 to x plus 20 simplifies to 2 to 3. Okay. Now, what we want to do with this is we want to make the ratio, this ratio here, we want to make that an equality so that we can find out a value of x. Okay. Now, we said that we want this ratio to be in equal parts, and we can scale down or we can scale up. I'm going to scale up because why not? A number that 2 and 3 both go into is 6. I want this to be in a ratio of 6 to 6, which means I want to times the left-hand side by 3 and times the right-hand side by 2. So if we do that to this, so I'm going to times this one by 3 and I times this one by 2, I'm going to get 3x take away 60 is equal to 2x plus 40. Now from there, that is an equation which you should be very accustomed to have seen. You should have seen this all over the place. Okay? We see which side has got more x's, take off or do the opposite, to the fewer amount of x's that there are. So I'm going to take away 2x from both sides, and then going to add 60 to both sides. And what I'm going to end up with is 3x take away 2x, which is an x. Negative 60 plus 60 is 0, so it disappears. And I'm going to have 100. Now what we can do here is we can use this to check whether this has worked. Okay, I'm going to grab a purple pen for a second. Now, if I have x is equal to 100, okay, I'm going to have 100 take away 20, which is 80, and 100 plus 20, which is 120. And I want to check that that simplifies to 2 to 3. Well, let's divide them by 10. That would give us 8 to 12. And let's divide it by 4. That would give us 2 to 3, which it does. There we go. We have found a value of x that simplifies to 2 to 3 by using an equality of our ratios, setting up an equation where things are equal to work out what x is equal to. Okay. Now, I'm going to give you a chance to work out the one on the right, which then should take us up to the 30 minutes mark of the video. So, here you go. Pause it, try it out, see how it goes. Okay, so hopefully you've given this a good go, and we're going to see now if we were right with what we want to do. I want to work, so similar before, I want to work out the value of x such that this simplifies to that. And what we need to do is make our ratios equal. Now, I've got two choices here. I can either scale up so that they both have the same, or I can scale down so that they both got the same. We scaled up in the left-hand one, so let's do the same here. I want to make it so that they're the same. And I want to make it so that they're in a ratio of 5 to 5. Which means that all I need to do with this one is times the left-hand side by 5. Then they will be equal. So, 5 lots of 2x is 10x. 5 lots of 40 is 200. And then this right-hand side actually stays the same because we didn't do anything with it. So now I need to know, right, these things are not just in a ratio, they are equal now. and I need to work out what the value of x is. So I'm going to take off 5x from both sides to give me 5x take away 200 is equal to 250. I'm going to add 200 onto both sides to get rid of the take away 200, which tells me that 5x equals 450, and then x is going to be 450 divided by 5, which is 90. Okay? So that takes us through 3 separate skills, if you like, that you can use with ratios, but you could effectively use in all 3 different parts of a problem. We took a look at the combining of our ratios, where we said, okay, we need to get this particular part to be the same in each of our ratios. We took a look at dividing in ratios, which we looked at, okay, where does the amount that we've been given go in terms of the problem? Is it everything? Is it one person? Is it a difference between 2 parts? And then making sure we knew what one part was worth, so we knew how much goes in each of these boxes. And then thinking about it in a more abstract way. And then we finished off by thinking, how do we make 2 sides of a ratio equal? Well, we scale them up so that they equal the same number or the same amount. Okay, 3 separate parts to dealing with ratios, but each have their place in terms of problem solving and working with problems. Again, we could have used our value to check that it does simplify to 1 to 5, but I'm pretty confident that it does. Okay, again, some questions here to do the same. There are only 4, and the answers right down at the bottom as well. Okay, pick your sections, know what it is that you want to work on through how well you did with these questions, so that you know how these 3 things work in terms of ratios. Okay? Happy revising, have a good one more week of your Easter holiday, and I will see you first lesson back.